Moving on to chapter 19 on page 278, 279, going forwards, we're looking at vectors. Now, you've come across vectors before in, well, certainly Key Stage 3 and also in section 19.3 where we came across column vectors. For example, we've got a column vector 4, 2. You may recall that means go 4 units across that way and 2 units up like that. So the net effect will be you create a vector 4, 2 like that with an arrow on it, and that is the vector 4, 2. So if we look at 4, 2 again, just to recall, the top number is the movement horizontally. It could be left or right. So if it's plus 4, you go 4 in the right direction. If it's minus 4, you go left in 4 units. So that's the horizontal movement. And the 2 will be 2 units up or 2 units down if it's minus 2. So that's the vertical movement. Now, is horizontal spelt with a Z or with an S? With a Z. Let's just change that. I think it's the same, but anyway. I've never spelled it that way in my life. Anyway, horizontal, across that way, vertical up or down. So let's just pick a few more vectors. If I want to do 3 minus 2, for example, and I want to start there. I want to go 1, 2, 3 across and 2 down, 1, 2 right there. Just do a quick join with that. And that's my vector 3 minus 2. Got to put an arrow on it because, like I said before back in 9.3, these can be considered as like one-way streets. This is the vector 3 minus 2, but the vector minus 3, 2 would be different. So if we start here, for example, minus 3, 2, go back, go to the left 3, 1, 2, 3, and 2 down, or 2 up, for example. That would be minus 3, 2. So I'm deliberately sort of flipping these around the other way, and this is what we're going to get. So minus 3, 2, we went 3 to the left and 2 up, and that will be completely parallel to the vector 3 minus 2. As you can see, they are completely parallel, but you can see the road's pointing around the other way. It's a different one-way street, so to speak. Alright, so recap: top number left or right, bottom number up or down, horizontal, vertical. Now let's extend to where we've not been before. If I look at vector, say 2, 3, you know that means 2 across and 3 up. Let's just draw it quickly using this facility. So 2 across, 3 up, 1, 2, 3. So that's that on there with an arrow on it. Alright, that's vector 2, 3. If I want to look at vector 4, 6, for example, so 4, 6, it's clearly, dodgy pen, it's clearly going to be 4 along, 6 up. So let's just start here again. 4 along, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Now what we can see clearly in these two vectors is that they are both parallel to each other, although the magnitude is different, the bigness, the size of them. So even though they have the same direction, the magnitude of this vector here is twice as big as the magnitude of vector 2, 3. Now, how do we prove it mathematically? If I was to, if you like, factorize 4, 6, and I've got, that'd be like having 2 lots of 2, 3. Is that alright? So instead of going 2, 3 and 2, 3, the net effect would be to go 4 across and 6 up. So is that okay? So if this was the vector, for example, little vector A, this will be called little vector 2A because it's twice as big as the original one-way street 2, 3. Is that alright? So if you end up in a situation where you're comparing drawn vectors, then you can tell if they're parallel not just by looking at them, but by doing a simple factorization of the larger vector to see if this is in fact the multiple of the other. So the vector 2 bracket 2, 3 is the word multiple. What's the best word to use? Yeah, is a multiple of 2, 3 itself. This proves they are parallel. Alright, so in terms of are they parallel, aren't they parallel, if there is a common element you can draw out of it, common factor, for example 2 here, then we can see that 2 lots of 2, 3 is a multiple of 1 lot of 2, 3. So 1 lot of this little journey line, 1 lot of this drawn vector is, and if you multiply by 2, you end up with 2 lots, and you can see they're parallel still, same direction. Now, the same is also true if it happens to go in a different direction, although maintaining its parallelness. So, for example, if I look at this vector here again, that would be vector 3, 2. I went 3 across and 2 up. Put an arrow on it. And 3, 2. If I want to then draw this vector, 3, 2 again, but this time it's going this way, that will be minus 3, minus 2. Is that alright? So 3, 2 is clearly parallel to minus 3, minus 2. How would I prove that they're parallel using factors? Well, if I take out minus 1 from this one, it would be minus lots of 3, 2. In fact, being algebra, I don't need to put a minus 1 in front of it if I just put a negative there. So minus 1 times 3, minus 3, minus 1 times 2, minus 2. Therefore, this vector here, column vector 3, 2, and this column vector here, minus bracket 3, 2, prove that the 3, 2 is common to both these vectors, and therefore that vector is parallel to that vector. So if for example, this was called vector, I don't know, B, this will be called vector minus B. Alright, so what have we done? Column vectors, horizontal, top number, vertical, bottom number. They're parallel if you could factorize and get a multiple and prove that one's the multiple of another. Therefore, the base vector, for want of a better term, for example, this and this are the same, although this one is twice as big as the original smaller 2, 3 vector. If you can get a common factor out of the vector, for example 2 here, and prove that 2, 3 is the same as 2, 3 over here, then 2, 3 will be parallel to vector 2. Then 2 lots of 2, 3 are clearly parallel to 1 lot of 2, 3, but 2 lots of 2, 3 will have twice the magnitude. And this 2, I've been calling it a multiple, it's actually called a scalar. In other words, it is the factor by which I scale up the common vector, and that's all it is really. I think they call it scalar in the book as well. Anyway, something I know is true anyway, that's a scalar. Now I'll just pause for a minute. So I think I'll leave it at this point there, and the word scalar is completely correct, multiple or scalar. That's it. So please revise 9.3, where we actually moved shapes around a grid using certain vectors or column vectors, and we translated them. Here we're looking at vectors in much more detail as single journeys up a line in a given direction having a certain magnitude or bigness, and the bigness is determined by the size of the numbers within each part of the vector. The 4 and the 6, for example, being twice as big as the 2 and the 3. And of course, even the 4 and the 6 in combination determine the direction in which that vector is going to point. So that's it. And we'll go and do some real questions. This will make much better sense. Again, on to do some real questions. These are just some general ideas to get you started. So see you in the next video.